Good morning all of you. Today we'll be doing elementary particles and then the various interactions they'll be participating, and we'll work out certain conservation laws which are obeyed by these elementary particle interactions. So let us first classify them, briefly classify all the elementary particles. So as we all know that prior to particle physics, we were all happy with electron, proton, neutron, and then in beta decay came along neutrino. But these were not the particles which were just the particles. The particles, further particles were discovered, such as muon, pion, kaon, sigma particles, so on and so forth. So all these particles emerged as a result of experiments in accelerators. So as of today, there are a few hundreds of particles, elementary particles, which we can say that they are all constituting the nuclear regime. Okay, the nucleus does not just have electron, proton, neutron, neutrino, but it has, when we smash an atom and thereby a nucleus by high energy particles in accelerators, it results in a large number of particles which number to something like a few hundreds of particles. So there aren't enough, a nomenclature problem has come now. So we just put some numbers followed by some alphabets. Okay, so all these particles, let us try to classify them. See, all these particles can basically be classified into bosons and fermions. As you all know, bosons are integer spin particles and they follow Bose-Einstein statistics, and fermions are half integer spin particles, they follow Pauli's exclusion principle. So the basic classification is this. All the particles we are divided into bosons and fermions. So examples of certain bosons are, we have the usual photons which we know, the familiar photons. We are more familiar with photons. So photons, they are having spin 1, mass 0. So they are mass 0, spin 1 bosons. Then we have W plus minus bosons which have spin 1 and mass 81 JeV, giga electron volt per c square. Okay, so these are the mass units. Gluons have mass 0 and spin 1, then gravitons mass 0, spin 2, then Z bosons which are spin 1 and the mass is 93 JeV. Okay, JeV is a unit of mass, JeV per c square. So for our elementary particles we use the units like this, JeV or million electron volt. So I did not write by c square, so it is, the units are, when I write JeV it means that. So these are all the elementary particles which are bosons. Then the second group of particles is fermions, which are half integer spin particles. Under these we have examples. I am just giving examples. There are many other hundreds of particles which happen to be fermions. So a few familiar ones I am just showing you. So like examples are proton, electron, neutron, apeiron, so on and so forth. So their masses are different. This is the heaviest one. So this is known as a hyperon. So any particle whose mass is greater than the mass of the neutron is known as a hyperon. Okay. So these are examples of fermions. Okay. Now, so all the particles can either be bosons and fermions, and these particles, they interact in certain elementary particle interactions which we are going to do. So we have to see what type of interactions these various particles are participating in, and we have to explain what is experimentally observed in the labs, in the accelerators. Okay, so experimental results we want to explain, that is the ultimate motto for us. So these particle interactions, let us see that we will classify the interactions. So as all of us know that any elementary particle interaction can be classified into four classes, four types of interactions. The first type is strong interactions. These strong interactions, as you all know, they are the interactions which are operate in a nucleus. Okay, a nucleus which is of the size of 1 Fermi is able to accommodate protons, neutrons and all, and it is holding together or it is stable because of these strong interactions. So strong interaction forces are the ones which are responsible for keeping the nucleus together, and they are independent of charge and they are short range forces. So these strong forces will come into existence only when we put the nucleons within the distance of 1 Fermi, that is 10 power minus 15 meter. Beyond that, strong interactions do not work. Okay, so we say that the range of strong interactions is 10 to the minus 20 meter to 10 to the minus 23 meter. This is the range. So the strong interaction operates within these distances. Then particles on which strong force acts, we call them as hadrons. So for examples of hadrons are protons, neutrons, pions, sigma particles, so on and so forth. So these are a few particles which participate in which are known as hadrons and on which strong force acts. So, and the coupling, every interaction is characterized by a coupling constant, and for strong interactions the coupling constant happens to be F squared by H cross C, where F is the strong interaction coupling constant. And the lifetime of these, the typical lifetime of these strong interactions is extremely small, and it will be of the range of 10 to the minus 20 seconds to 10 to the minus 23 seconds. Okay? The range, this is something like 10 to the minus 50. Yeah. This is the range and this is the lifetime. So something like this. This is 20. So this is the typical lifetime of strong interactions. Next, the next type of force is, these are known as the four fundamental forces, right? So the first one we finished. Now the second one, the second type is known as electromagnetic interactions. The range of these electromagnetic interactions is from 0 to infinity. As you all know, electromagnetic interaction is ruled by the Coulomb's law. The force between, it's a force which acts between charged particles, and the force will be like Coulomb's force. So that is, if the force acting between two charged particles given by Coulomb's law, that is Q1 Q2 by 4 pi epsilon naught r square. So it's the inverse square law. The force obeys inverse square law. So electromagnetic interactions are governed by that force which is inverse square law, and the typical lifetime of electromagnetic interaction is 10 to the minus 15 seconds to 10 to the minus 18 seconds. Then examples of particles which participate in electromagnetic interactions are, you familiar? Gamma, photons. Gamma is photon. Photons, electrons, protons, so on and so forth. Now coupling constant. The coupling constant of electromagnetic interactions is nothing but E squared over H cross C, which is known as the coupling constant, which is 1 over 137. Next one. The third force, the third fundamental force is weak interactions, or the third type of interactions, third type of fundamental interactions are weak interactions. Weak interactions are 10 to the minus 13 times weaker than the strength of strong interactions. That's why they are called as weak. So compared to the strong interaction force, the weak interaction force is 10 to the minus 13 times. So strong interaction force divided by 10 to the 13. So it's very, very weak. So we call it weak. So weak interactions, as you all know, they are responsible for beta decay, where parity won't be conserved. So it's a different type of interaction. So the particles which are participating in this interaction have to obey certain laws and have to follow certain rules. So these we call it as weak interactions. So the typical lifetime of weak interactions is 10 to the minus 10 second to 15 minutes. So you can see all this in when you do in beta decay. So examples of particles which participate in weak interactions are electron neutrino, muon and muon neutrino, tau and nu tau. So all these particles participate in weak interactions, and these have a name called leptons. So what are leptons? Leptons are all those particles on which strong interactions do not operate. These leptons are particles on which strong interactions do not participate, and they are called leptons or light particles. So what are they? I have written it in the form of a table. Leptons, main leptons are electron, muon and tau particle. Electron is 0.55 MeV mass, charge is -1. Muon is mu minus is 105.7 MeV and charge is -1. Tau minus is 177 MeV -1. So the heaviest lepton is tau particle. Lightest one is this one. So and what about the neutrinos? There are neutrinos associated with these particles, which are electron neutrino, muon neutrino and tau neutrino. So these particles are found to come out in beta decay. You can see for example in beta decay neutrino comes and antineutrino comes. So in various other weak interactions also you see these particles. So these are massless particles, massless fermions they are, okay. And also all these leptons are followed, they also have their antiparticles, which are the antiparticle of electron is positron, antiparticle of mu minus is mu plus, and antiparticle of tau minus is tau plus. So an antiparticle has all the properties identical to the particle except the charge. So mass, spin, everything will be the same, but the charge will be opposite, then we call it as an antiparticle. So these are the antileptons, and these are their corresponding neutrinos. So this is the lepton corresponding to the neutrino corresponding to positron is positron neutrino, which we call it as antineutrino. So these are antineutrinos. These are neutrinos associated with antiparticles. So we call them as antineutrinos. So this is antineutrino, anti-electron neutrino, anti-mu neutrino, anti-tau neutrino. So we denote them as with a bar. Now, so we have finished with leptons, which are the participants in weak interactions. Other particles also will come in weak interactions, but major particles are these. Gravitational, the last interaction is gravitational interaction. This is the last type of fundamental force. So this is 10 to the minus 38 times the strength of strong interaction. So this is the weakest one, the gravitational force, but we call this as weakest, and because gravitational interactions are so weak that everything comes under this, so we don't bother about calling this as a weak. So within the elementary particle interaction, this is the weakest, so we call this as weak interactions. So gravitational interactions we are talking about, they are 10 to the minus 38 times the strength of strong interactions, and their coupling constant is k times m squared by h cross c. The coupling constant, you can see always the coupling constant will have a e squared by h cross c, m squared, here gravitational constant mass plays the role of charge, so m squared by h cross c with a k, and where k is the Newton's constant. And the coupling constant for strong force also, you see it will have F squared, which is the coupling, F is the coupling constant which is characteristic of strong interactions, that is strong intrinsic coupling constant F squared by h cross c. So always the coupling constant will have this form, this form, this form and this form. So weak interactions is yet to, we cannot, so weak interaction coupling constant we will do it. So weak interactions comes under something known as V minus A theory. So we will come to it later.